In the previous video, I argued that this electrical circuit here, with a resistor and a capacitor in parallel, can represent the membrane of an excitable cell. And just to remind you, the capacitance, or the capacitor in the circuit, corresponds to the insulating properties of the lipid bilayer in the cell membrane, which is a good electrical insulator, and therefore gives the membrane capacitive properties. The resistor represents the ion channels that allow ions to move through the membrane and allow for changes in the membrane potential. And this battery here represents the sodium-potassium pumps that maintain a electrical gradient across the membrane. So, for example, there is more sodium ions outside the cell than inside the cell, and this potential that is sort of there at baseline and is maintained by these ion pumps has to be taken into account, and that is put there. Okay, so we know what all the components of the circuit are. Oh, and I guess the last thing that I should say is that Vm represents the membrane potential, represents the difference in voltage across from the extracellular and intracellular compartments. Okay, so now that we have this circuit, how can we create a mathematical equation that will tell us a little bit more about its dynamics? Well, there's two basic equations that I'm going to talk about in this video that will lead us to a dynamical system that we can study further. The first is the law of capacitance, and that states that Q equals CV. And I talked about this briefly in the previous video. So this equation is referring to this component of the capacitor within our circuit. Q represents the charge, or the difference in charge across the membrane. So if you had positive charges on this side of the capacitor and negative charges on this side, Q represents that differential distribution of charge. So that's what Q is. C is the capacitance, which is related to the insulating properties of the membrane, and that's just a constant that doesn't change over time, sort of an intrinsic property of the membrane. And V here is the membrane potential, which before I called Vm. In this video, I'm going to drop the subscript M just for brevity's sake. In a later video, I might sort of clear up some of these subscripts. In this video, I'm going to be a little bit sloppy and just sort of talk broadly. But in a later video, I might go back and talk about exactly what I mean when I have that subscript M. Okay, so this is the law of capacitance, and you can see that there is a membrane potential here. And if we want to solve for the dynamics of that membrane potential, we're going to want to use a differential equation, similar to what we did in the first few videos, I guess, in this mini unit. So to get a differential equation, I'm going to differentiate both sides with respect to time. So dq dt. The change in charge over time. So C is a constant, so when I differentiate, that just comes out, and now I have dV dt. Okay, and if you, those of you who have taken physics, you'll maybe realize automatically dq dt is the change in charge over time, and that is the definition of current. And current is denoted by I. Okay, so this, I'm going to call it IC for now. This is the current and the capacitive current, because this law here, law of capacitance, again, is referring to this part of the electrical circuit. So the capacitive current is equal to, well, just C dV dt. And that's pretty much it. Okay, so this is the first equation that I want to talk about, so I'm going to box that off, so we're going to come back to it. And right next to it, I want to talk about the current in this part of the circuit. So, again, this is a very simple law. It's called Ohm's law, and that's usually expressed as V equals IR. In this case, I'm going to say delta V equals IR. So delta V being the drop in voltage across the resistor. And note that this change in voltage is not necessarily equal to the total change in voltage, or Vm. It's the drop in voltage across the resistor, which is subtle, but it's not necessarily the same. So what is the drop in voltage across this resistor? Well, this fictive battery, for the purposes of this lecture, I'm going to say the fictive battery has a voltage potential E. In the previous video, I denoted this as V rest, because the voltage of this fictive battery essentially sets, you can think of it as the steady state voltage for this passive membrane, or basically the voltage that this membrane would be at if you didn't perturb it in any way. So in this video I'm just going to say E because E is easier to write than V rest. Okay, so the change in voltage across the resistor is equal to V minus E. So V minus E equals IR. So the current running across the resistor, which I will denote as I sub R, is equal to V minus E over R. Okay, so this is the second result. So we've solved for the current across the capacitor and the current across the resistor. And the last part of this video, I will combine these two to look at the overall dynamics of this circuit. Just erase this quickly. Okay, so the final step in our analysis. So before we solved for IC, which was the current, capacitive current, IR, the current running across the resistor, and due to conservation of current, these two currents in the network must sum to zero. If they don't sum to zero, that violates, basic laws of physics. So this is the final physical equation that you sort of have to take my word on. Again, I will try to provide links to basic electrical circuits and physics videos online that will explain some of the more underlying physics of this process. But for now, I think this is, it's pretty simple, and hopefully you have an intuition for this, and if you've taken any physics, you'll follow me right along. Okay, so we said before that IC is equal to C times dV dt, and IR is equal to V minus E over R. And we've said that this must sum to zero. Well, if we have dV dt, I'm just going to rearrange this a little bit. So we have dV dt on the right side, and when I subtract from the other side, I'm just going to switch the E and the V. So now I have E minus V over R. And so R and C, as I sort of mentioned before, R and C we are assuming to be constant at the moment. C will always be a constant. In the future, the resistance of the membrane is not going to be constant. It's actually going to be changing when, let's say, a ion channel opens or closes, for example. But for now, we're thinking both of them as constant. I'm going to multiply both sides by R, and say RC dV dt equals E minus V. And when I put the equation in this form, you should realize that if you've seen the earlier videos, this form is actually very similar to something that we saw before when we were looking at the dynamics of simple molecules. And to make that point more clearly, I will make the following substitutions. We will say tau equals RC, and we will say VSS equals E. If we make these two substitutions into this equation, then we get tau dV dt equals V steady state minus V. And this equation is exactly what we talked about in the videos before we started talking about the membrane equation. The only difference being that now the dynamic variable is V, representing the voltage, rather than X. So this should be encouraging to you, because if you understood the videos before, now we're on familiar ground, and we can begin to pick apart this differential equation in similar ways. So this parallel is nice, and I think it's something that you might not necessarily draw the connection between the membrane equation and the molecular systems biology stuff that we were talking about in the earlier video. So that was why I wanted to emphasize and start that to make that connection a little bit more, just that connection a little more concrete in these videos. Okay, thank you for your time, and I'll see you in the next video.